Alright, superstars, we are back to our topic 2, more derivative rules in line for today. The first function we're going to discuss is the exponential function. The exponential function is always defined to be e to the x. There are other, of course, functions that are exponential, 2 to the x, 3 to the x, but as we mentioned before, e to the x has that wonderful property that its derivative is beautiful. And as we'll see next class on day 22, all the other exponential functions aren't quite as nice. So we generally tend to stick with e to the x. You need to know the others, but this one's just a little nicer to work with, so why not? You'll even notice that it's usually referred to as the exponential function, and so if someone says exp of like 4, what they really mean is e to the fourth. So it even has its own exp. Your calculators, a lot of the inspires, you can type exp and it means e to the power of. And then the second function we're going to discuss is, of course, the one that immediately follows our exponential function, which is the natural log function. It should make sense that they go hand in hand, and since the exponential function has a nice derivative, you should expect that to be true for the natural log function, and oh, you'd be right, it does have a very nice derivative. And it turns out that all the other logs do not have nice derivatives. So let's get to it. Your opener for today is to use version 1 of the chain rule. And a reminder, version 1 says if you have a function dy dx where one function is inside the other, then you perform a u substitution and you take the derivative of that function with the u substitution with respect to u. But then you need to remember to multiply by the derivative of your u substitution with respect to x. So go ahead and try this, and then once you're done, you can hit play and check back in on this. Well, hopefully you have unpaused at this point, and we can take a quick peek. So if this is our u substitution, then that gives us two functions. It gives us y equals e to the u, because we replaced all of this with u. And so that means that dy du is going to be equal to, well, just itself, right? E to the u. That's the derivative of e to the u power is just itself. However, we also have, and I'll try to make this work down below, we also have the u substitution, which is u equals 4x squared minus 3x, which implies that the derivative of our u substitution with respect to x is 8x minus 3. Putting this all together then, that is going to tell us that dy dx equals the derivative of the y function with respect to u, and I'm going to make that reverse substitution right now, so e to the, instead of this, I'm going to replace the u with what u was, which was 4x squared minus 3x, times the derivative of our u substitution, which is 8x minus 3. And if you write it like this, you will 100% get the not right answer, because we need to make sure that we multiply the entirety of this first function, though we don't need parentheses there, by the derivative of our substitution. And so we do need parentheses by 8x minus 3, right? That would actually mean that we take this and distribute to the 8x and distribute to the minus 3. If we left the parentheses off, that would not be apparent. In fact, our statement there would be incorrect, and you would lose points for it. So it shouldn't shock you then too much to learn that we've actually been doing e to the power of something and using the chain rule this whole time. In particular, 3 examples that you don't need to write down. In fact, I'm going to do them in my infinite paper on the right. When you're asked to take the derivative of e to the x, the derivative is e to the x, but it's technically times the derivative of x, which is 1. The second derivative that we worked with was e to the 2x. And we said e to the 2x was 2e to the 2x, keep that in mind, but really what we're doing is it becomes e to the 2x times the derivative of the power, right? So knowing that, then we can really generalize our derivative of e to the x, and your textbook uses something similar to this, and I'll explain this in a second too. We can say if you're asked to take the derivative of e to some function, then the derivative is e to that function times the derivative of that function, right? Your textbook says something similar, but your textbook says if you do d dx of e to the u, and this is where things get confusing, they mean u is a function. They don't mean u is a variable, and we know it's not the variable because this is x. This is u. U is standing in for something. Then they tell you that the derivative is e to the u times u prime, so times the derivative of whatever your function is. I like this notation a little bit more. I think it's a little more clear, but it's ultimately up to you. Now, we have three functions down below. Your goal is to find the derivative of each one of these, and then once you're done, go ahead and check back in. You've probably unpaused at this point, so let's take a look and see how we did. Our first one, I think we don't need the u substitution. We can probably do this all at once. We get e to the x squared plus 3x when we take the derivative. That stays exactly the same. But then we need to multiply by the derivative of our power. And this thing we're multiplying by is not a power anymore, and it is 2x plus 3. Okay. You could see some people write that in front of the e as well, but you do still need the parentheses. What about the second one? Well, the derivative of e to some function is itself. That doesn't change. However, we do need to multiply by the derivative of this. But the derivative of cosine of x squared is in itself a chain-ruled function, and it's a function composed into another. So we do the derivative of the outside first, which is negative sine of sine, and then keep the inside the same. But then, because we kept the inside the same, we need to account for that and use the chain rule there as well. If you wanted to put this all together, I'm not sure maybe the best way to write this. Maybe it'd be something like negative 2x sine of x squared times e to the cosine of x squared. Something like that, give or take. And then last but not least. Whoa, this looks gnarly. I don't really think I want to do the derivative of that because as written we'd have to use the product rule. There's two functions each with x that are multiplying. Let's maybe try to combine these together first. I'm thinking we could treat this as e times x to the 1/2 times e to the 2 times x to the 1/2. I see the same base there, which means we can of course add or sum our exponents. Okay, don't forget there's an invisible 1 here. We have 1 of these x to the 1/2 plus 2 more. I think that's going to give us an actual function of y equals e 3x to the 1/2. I would much rather take the derivative of this than that. The first one, we need the product rule and the chain rule. Sounds awful. This one I think we can probably tackle just by using our product rule, or I'm sorry, our rule for e. So the derivative is always itself, 3 times x to the 1/2 times the derivative of the power, which is, well, 3 stays the same, it's multiplying, and we get 1/2 x to the negative 1/2. If you wanted to write that in a little bit more of a friendly form, we're not going to be able to do too much. This 3 and this e to the 3, and all we can write as a square root of x all have positive powers, but then the rest of this part in red is going to drop down here. 1/2, think of 1/2, really it's just a 2 in the denominator. So it becomes, I think, 2 times the square root of x. And there we go. You are now masters at doing the derivative of e to any power. But as mentioned before, we were already pretty good with e, so it should make sense that we're going to present now its inverse function. And of course, the inverse function of e to the x is the natural log of x. When I write natural log, I don't write it like this because that looks like a 1, and then you're like, what's n of x? I always write my L as a cursive, but then sometimes it ends up looking like an h, and you're like, what is h of x? No, it's ln of x. So although we know how to find the derivative of e to the x, we don't know, I think, even the first place to start with the natural log. If I said, please go ahead and take the derivative of this, you'd say, please unenroll me from this class. Now, we might always be thinking that, but hopefully not. So let's go ahead and solve that little conundrum so that we can stay enrolled in this class. We have f of x equals the natural log of x. One really clever thing that we can do here is exponentiate each side, which really means do e to the power of each side. And the reason we're doing that is because we know how to take the derivative of e to some power. And we also know that our end goal is to figure out what f prime of x is. And so what that's going to let us do is at least take the derivative of this side, and I bet you might notice here what's going to happen to this right side. We remember these are inverses, so we're going to be left with e to f of x on the left, but these undo each other and the x drops down and just gives us this piece on the right. And that's awesome, because now we have functions scattered all over the place that we all know how to take the derivative of every single one. So how do we do it? Well, let's take the derivative of each side here. So I'll take the derivative of this side, and I'll do that in yellow. We know it's e to the f of x, where the derivative of e to something is always the same, but then practicing our opener, we do the derivative of the power f prime of x equals, and then we need to take the derivative of the right side, but the derivative of x with respect to x is just 1. Cool. Now, what are we actually trying to solve for? Well, we want to know what does f prime of x equal, so we should probably isolate f prime of x. And I think that's easy enough, right? We just divide this guy over to the other side, which is where this piece comes from. And then we've really found the derivative of the natural log of x. This is the derivative. However, we can make it look a little nicer. It's usually frowned upon if you take the derivative to have f of x standing in the original or in the derivatives equation. It's kind of, I don't know, cyclical here. So what we're going to do instead is we know what f of x equals, don't we? We, I think, know that f of x from the very beginning is the same as natural log of x. So let's take this then and let's replace, right, e to the f of x with e to the natural log of x, or, canceling down, 1 over x. And this is really a pretty wild function. It tells you when you take the derivative of the natural log of x, its derivative is 1 over x. And the reason that's wild is because think back to trig functions. The derivative of every trig function that we saw so far was another trig function. The derivative of sine, cosine, derivative of tangent, secant squared. The derivative of another transcendental function, that's what these guys are called. There's all sorts of cool videos on why they're called transcendental functions. But the derivative of e to a power is another transcendental function. It's e to a power again. But now we have another one of these, this natural log of x. And when we take the derivative of this transcendental function, we get a non-transcendental function. We get the rational function 1 over x. And you should be pretty excited. You're like, I don't like logs. Cool. Take the derivative of logs, and then you don't have to deal with them anymore. And that, I think, is pretty cool. Now, is there more? Well, there's a little bit more. You need to remember a few properties of logs. In particular, if you have a constant, a multiplying by any log, I use natural log in this case, don't forget that we can rewrite that as the natural log of x to the a power. In fact, this is why we first introduced logs. It helped us solve exponential equations. We were able to do the log, and then using that rule, we were able to remove the power and move it to the front. Now, well, what that means is that those two are equal. So if you're asked to take the derivative of 2 times the natural log of x and compare it to the natural log of 2x's derivative, shouldn't they be the same? Because you're allowed to bring the 2 in here. That's manipulating the equation, not changing it. And so they're really the same graph. If you graph them, they look identical. And I think that means our derivative should be equal. So let's take a look. When you do the derivative of this first one, 2 is a constant, so we can probably factor that out. And then when we do the derivative of natural log, oh, that's 1 over x. We just learned that. Or if we simplify, we get 2 over x. So the derivative of 2 times the natural log of x is 2 divided by x. Nifty. Does that hold over here? Let's see, natural log. Oh, didn't we learn that this should just be 1 over, well, this is x squared, so maybe 1 over x squared? But wait, these functions are equal. Is 1 over x squared equal to 2 over x? I don't think so. I think we made a mistake somewhere. Oh, but what's our mistake? Maybe we might remember from our chain rule practice up above that we know the derivative of the natural log of x, and this is x squared. So what if I replaced x squared with u and asked you to take the derivative of the natural log of u? Well, our chain rule tells us it's going to be 1 over u, the derivative of the function with u in it, times the derivative of our u substitution, which we write as du dx. And so replacing all of this, my original u substitution was for x squared. Du dx, the derivative of this guy, right? Du dx is 2x, so we need an extra 2x here. The chain rule is absolutely in effect. The natural log is 1 over whatever's inside. But then we didn't take the derivative of what was inside, so we need to multiply by that at the end. That's our chain rule. And then I think cleaning this up, it might be a little more clear as to why these two answers match, right? X to the first x squared, we're going to take away one of these, and that leaves us with 2 divided by x. And that shows us that these functions that are identical by log rules do indeed have identical derivatives, even if they didn't look identical at the beginning. And so that actually gives us an even nicer derivative, or maybe not nicer, but even more complete derivative for natural log. The same way that we did this with e to the x. And wow, I'm noticing, look at my overuse of parentheses here, it's super cute. So when we take the derivative of this, we take whatever function's inside, in this case it's f of x, and it becomes 1 divided by whatever's inside. So don't think 1 over x, think 1 divided by the interior function. But then, because we left the interior function the same, we only did the derivative of natural log, that's what caused this, then we need to multiply by the derivative of what was inside, which is f prime of x. So natural log is 1 divided by what's inside times the derivative of what's inside. So are we done with natural log? Well, almost. I think there's a little bit more to it. For example, what if we were asked to find y prime of -2 given this natural log? Well, we could, in order to do this, in order to find y prime of something, we need to find y prime of x. So y prime of x is the derivative of this guy, which is 1 over x. All right, good so far. And then y prime of -2 is, of course, 1 divided by -2. And honestly, I should have done this better. I should have said it's the derivative of what's inside times the derivative of what was inside. And technically there should be a times 1, but we don't need to write that. So I think either way, y prime of -2 is -1/2. Cool. But is it actually cool? Because I think if you look at the problem on the left and you put this in context of the original graph, what this is saying is at x equals -2, that was our x, our input, right? The slope of y equals natural log of x is -1/2. Well, why is that weird? Let's maybe picture that graph of the natural log of x. I have it up on the screen right now. And so we can see that this is 1, 0, any log of 1 is 0. We just found the slope at -2. That's way over here. Well, if I look at this graph, we might remember that the natural log never goes negative. It doesn't even get to 0. It approaches an asymptote at 0. So what's the issue here? Well, I think the issue here is that my answer makes no sense. Why would this derivative give me an answer that doesn't make sense with my original problem? And so we come to the first time where these derivatives are kind of lying to us. Well, what really happens is this connection between the original function we took the derivative of and this new function. We're saying they're equal. We put an equal sign here. And with an equal sign, that means that they should probably have the same domain, right? If we say here's one function, here's the same function, then the values that I plug in for x should work in each function. Well, compare these two. Now, I've written these in set notation. I'm not sure if you're comfortable with set notation, so we can probably take a look here. I've shown the domain of the natural log function and the domain of 1 over x. The domain of natural log of x is such that x must be, this is our such that symbol, such that x must be greater than 0. That tells us in natural log we are only allowed to use x's that are greater than 0. However, our domain of the rational parent function 1 over x is such that x's cannot be equal to 0. And I think these two domains do not match, right? In fact, this domain is twice as large as this one. This is all the numbers greater than 0. This is all the numbers greater than 0 and less than 0. They're both infinitely large. One's just doubly infinitely large. Try that on for size. So Is there a way that we can adjust the natural log function so that its domain matches the domain of its derivative? Well, let's try taking the derivative of the natural log of negative x. I think this has got to be some chain rule here. We're going to do 1 over what was inside times the derivative of what was inside. The derivative of negative x, I think, is negative 1. And then if we clean this up, you'll probably notice that our two negatives turn into a positive, and we're just left with 1 over x. And I think over here, the derivative of natural log of x, we know is just 1 over x times 1, but really just 1 over x. So this is interesting because it turns out that the derivative of the natural log of negative x and natural log of x have the same derivative. Well, are there any values for 1 over x that don't work in at least one of these functions? For example, I think we're allowed to use positive numbers in here, and you can also use all the positive numbers over here. We can't use negatives up here because natural logs of negatives don't exist. We can use negatives down here, and I'll show the negatives in red, but if you plug a negative in here, you can also put it in here, because if you try a negative and there's already a negative, they cancel and make a positive, and life is good again. Okay, so how do we condense two functions like that where you can use both negatives and positives because they both turn into a positive? Well, oftentimes the natural log function is rewritten as the natural log of the absolute value of x. And this should make a lot of sense. It basically means whatever value you plug in for x turns positive, and then it has the same derivative. So it's basically combining these two functions together into one superfunction. And it's saying when you do the derivative of that superfunction, it's 1 over x, because the two functions that make it up also have derivatives of 1 divided by x. Now, this may not seem super important first semester, but it's going to be really important second semester when we start working backwards and we say, what's the antiderivative? What's the, if you work backwards from 1 over x, what did you take the derivative of? And you're really going to have to remember that absolute value. So, long story short, too late, name that movie. Our ultimate summary. Two things. If you are asked to take the derivative of the absolute value of f of x, then it is just 1 divided by what was inside times the derivative of what was inside. And notice there is no absolute value in the derivative. So even though there might be absolute value here, it does not stick in the derivative, and that has to do with properties of logs. Of course, if you just are asked to take the derivative of the natural log of f of x, no absolute value, it is still 1 divided by f of x times f prime of x. So again, any sort of natural log, whether it's absolute value or not, and this is really the only time we're going to talk too much about the derivative of absolute value as a function. Maybe we'll do a little bit more with graphs later on, but it turns out that it does not matter at all. You get the same derivative, absolute value or not. Okay? Now, the last 2 pages of this are really for you to work through. There are 9 tricky problems here, and all the answers have been given to you, right? So it says find the derivative here, and the derivative is down here. There are 2 tricks to this. First, you need to be really confident with your derivative rules. Power rule, product rule, quotient rule, chain rule, trig functions, natural log, e to the x, exponentials. Oh, we don't know exponentials, but you get the idea. Whew, there's a lot. And then the second part is, if you're able to get that derivative at the beginning, that is awesome. I think that's 9/10 of the battle. However, matching the answers at the bottom can definitely be a little tricky. And so we do need some algebra practice here too, because sometimes those multiple choice problems throw a nice wrench in the plans, and you do need to be able to simplify. So take some time, try all 9 of the problems first. If you get stuck on one, star it. You can come back to it later. You can watch the video later, but try them all first. Dedicate, well, let's see, 9 times 2. Dedicate at least 18, probably 20 minutes, if not 30 on these. If you move faster, that's fine. And then at the end, come back, unpause this, and then see how I do them, skimming through, making sure you don't spend too much time on this video. Okay, hopefully we have now unpaused. I'm going to go ahead and work through each of these. Again, be intelligent about this. If you already knew how to do the first couple, then make sure you hit the fast forward button, watched it 2 times, 4 times speed. Don't just sit around wasting 45 minutes of your time, and I'll try to go through pretty quickly. If I go through too fast, make sure that you go through and email me so that I can get back to you. All right, derivative here. Oh, this is one of our new ones. Exciting. Derivative of natural log is 1 over whatever's inside, secant of x, times the derivative of secant. Hopefully you guys have these on note cards. We're going to spend a lot of time next week remembering these derivatives because you do not get a formula sheet on your test. So make sure we're ready there. Okay, 1 divided by secant times the derivative of secant, which is secant of x, tangent of x. Something you need to memorize. And then also realize that there was absolute value here, but we just learned that if there's absolute value in natural log, it does not matter. Well, can we clean this up? Sure. Secant, cancel secant, and I think that gives us that f prime of x is tangent of x, and we have crushed it. Smiley face to fill the space. All right, next one. Let's see. I see one function divided by another. I think this means the quotient rule. So we have our top function and our bottom function. And my colors did not catch up, so second try. Catch up, red, get it. Cool. Better than mustard. Top function. F prime of x. Derivative of the top function. The derivative of natural log of x squared is 1 over what's inside times the derivative of what's inside. Keep the bottom function the same. Minus. Now we keep the top function the same. And we take the derivative of the bottom, 2x, and this is all, of course, divided by the denominator squared. All right, let's clean this up. I think instead of doing 2x and x squared and destroying that, why don't we just cancel out the x squared and the 1 over x squared? And I don't think we're going to do too much else from there, but let's see what that does for us. It gives us 2x minus 2x ln of x squared, all divided by x squared squared is x to the 4th. Okay, does that match our answer? No, it looks like they factored out a 2 and this reduced by 1. So I think we might want to factor out a 2x here. I think there's a 2x common to each of these terms. So if I steal a 2x, that leaves me with 1 as a placeholder, minus natural log of x squared, all divided by x to the 4th, which I'll write as x times x times x times x, just to make this last step easy to see. Hopefully you can tell that our x's will reduce, and I think we have found our wonderful answer. 2 times the quantity 1 minus natural log of x squared, all divided by x cubed. Gosh, we're good. All right, next one. Oh, buddy, this one's going to blow your brain, unless you did it right, and then my brain is blown in return. So well done there. Here we go. Derivative. Well, I see lots of functions. I see natural log on the outside, x minus 1 divided by x plus 1 on the inside, but our chain rule says do the derivative of the outside function first, which is, of course, 1 divided by what was inside, x minus 1 divided by x plus 1. Am I done? Oh no, I need to take the derivative of this inside function. How do I take the derivative of this inside function? Oh yeah, we have to use the quotient rule. Right, so let's look at our quotient rule here. Our quotient rule, I'll do a big set of parentheses so we can see we're doing our quotient rule. We do the derivative of the top function, and then we, of course, keep the bottom function the same. Minus in our quotient rule, keep the top function as it was, derivative of the bottom. And then, of course, we do the bottom function squared. Please tell me we can stop here. Oh, no, we have further to go. Well, how can we reduce this? A few things to note. First, we have 1 over a fraction, which of course gives us the reciprocal, x plus 1 divided by x minus 1. And then I'm going to drop the parentheses. I think everything will be even here. And it looks like the numerator up here becomes x plus 1, distribute the minus, minus x plus 1 divided by x plus 1 squared. What else can we clean up here? It looks like the x's here will cancel. 1 and 1 gives us 2. So I think we have f prime of x equals x plus 1 times, I'm going to bring just the 2 over with me. 1 and 1 made 2, right? Divided by x plus 1 squared times x minus 1. Slightly rearrange the order just so I think we can see this last step. Where our last step here, it looks like we have one of these x plus 1s up here and two of them down here. And then, very, very last, we keep the 2 on top, but now I have x plus 1 times x minus 1. That's a difference of squares, and when you multiply it all out, two inner terms cancel, and you end up with x squared minus 1. Whew, big sigh of relief there because I haven't screwed up too badly yet. However, now we get to this fourth one, and this fourth one is pretty tough. This one came out, maybe early 2000s or so. Ye all were just little wee babes. And it's pretty tricky. Not so much for the calculus, so the calculus isn't super easy, but it's also because of simplifying to this answer. I think is really tough. So let's see where it takes us. I see two functions here. I see x times 2x minus 3 to the 1/2. Let's pretend the square root isn't there. I mean, who wants that square root anyways? And I think because we have those two functions multiplying, we'll probably need the product rule here. So product rule wise, we do the derivative of x, which is 1. And then we keep the next one the same, so 2x minus 3 to the 1/2 power, plus for the product rule. Keep the first function the same, and then we get to the wild second derivative, or the derivative of the second function. The 1/2 comes down, 2x minus 3 stays the same, but we have to reduce the power by 1. But then wait, we kept the inside the same, so I think this is a chain rule buried in a product rule, and we need to do the derivative of 2x minus 3, which is just 2. Whew. Well, we're definitely not done. We've seen that answer down below, and it's way nicer than this guy. So what can we reduce here? I noticed that we have a 1/2 and a 2, and 1/2 of 2 is just 1, and we don't need to write that 1. So I think we can get rid of that part. That's nice. I think we can slightly clean this part up. We can say f prime of x equals, this will be 2x minus 3 to the 1/2, and I'm going to put this over 1. We can write anything over 1. We just don't need to write this one at all. Plus, this x is the only thing left with a positive exponent, so that stays up above, and we're going to move this 2x minus 3 to the denominator. Now, this still doesn't equal our end result down here. Our end result is all one fraction, which means somehow they added these two fractions together. Math magic. Well, I think to add these two fractions together, we need common denominators. And to give them common denominators, I think the 1 will be really easy to match over here. I think this 1 is missing a 2x minus 3 to the 1/2 power, which means we need to do the same to the numerator as well. Let's see how we can catch up here. Denominators are the same now, so I'll just write this as one big common denominator, 2x minus 3 to the 1/2 power. We are multiplying two terms that have the same base. The base is 2x minus 3, which means we can add the exponents. It becomes 2x minus 3, and then we add the exponents together. And then, of course, there's this friendly old x that's hanging out at the end. Okay, well, can we go any further? Sure, I think that the 1/2 plus 1/2 means that we just get 1 here, right? And we don't need to write a power of 1, so I'm seeing 2x minus 3, no parentheses, that's a power of 1, plus x, divided by 2x minus 3 to the 1/2. And finishing this off, I'm looking at 3x minus 3 divided by the square root of 2x minus 3. And I think we have our final match. Yeah, definitely a lot to do there. Hopefully this next one is easier. Let's see, it looks something, the screen is frozen. Just want to get an idea of the answer. There it is. Okay, let's see what we can do here. All right, the derivative of this guy. Well, I don't like the derivative being written like that with this weird little trig notation. That's just laziness, so let's write it out. This becomes the derivative of cosine of x cubed and all of that squared. Yeah, that looks pretty good. So let's go ahead and realize that there are three functions going on here. Our most outer function is the square, my next outer function is cosine, and my innermost function is x cubed. So it looks like three iterations of the chain rule here. We start with the outside. The 2 is going to come down, and it's going to leave the rest of everything unchanged. Cosine of x cubed to the first power. Now we need to tackle the derivative of the inside, but the derivative of the inside has two pieces, so we need to do the derivative of the outside of the inside, if that makes sense, and the derivative of cosine is negative sine. But then we need, of course, to keep or preserve the interior. But because we kept the interior the same, we need to multiply that derivative as well, which is 3x squared. Once we're here, putting it all together isn't too bad. We're going to take everything that can be multiplied and multiply it together, like the 2 and the negative and the 3x squared. I think that's 6, negative 6, it looks like. I think, yeah, we get negative 6x squared. And then we have this cosine of x cubed, the first power doesn't matter, and sine of x cubed. And notice we took this negative and moved it out front. And I think that's all we had to do on that one. So not too bad. Some chain rule inside of a chain rule inside of a chain rule, like those Russian nesting dolls, but not awful. Okay, problem 6. Two tricky parts for this problem, maybe 3. There is a chain rule, but I think that's the least tricky. The second trickiest is actually knowing the derivative of tangent. And then the last part that's tricky is knowing your trig values. So let's get to it. In order to find f prime of pi over 6, we first need to find f prime of x. When we do the derivative of this over here, I think that we are going to do the derivative of the outside first, and hopefully you remember the derivative of tangent is secant squared, and then we keep the 2x the same. But because we kept the 2x the same, we need to multiply by the derivative of that, and we end up here. However, having done this problem many times now, I find that students generally don't like to write the answer like this. They like to move or keep the 2 on top, and then instead of secant squared, I don't know a lot about secant squared, but I'm pretty good at its reciprocal, and the reciprocal of secant squared is, of course, cosine. So they prefer to write this problem like so, or actually, going even further, I probably should have said it's the cosine of 2x, all of that squared. Right, just moving the square to the outside. All right, well, what do we do next? I think we need to evaluate this at pi over 6. F prime of pi over 6 becomes 2 divided by the cosine of 2 times pi over 6, all of that squared, and now it just becomes simplifying. Well, when we do this 2 times pi over 6, notice we can cross-reduce, and that leaves me really with the cosine of pi over 3 and then squared. We do need to evaluate the cosine of pi over 3. Trig values. Pi over 3, let's see, pi over 3 is in the first quadrant. 180 divided by 3 gives me a 60-degree reference angle. So we have a triangle that looks something like this, and we should be comfortable with our 30, 60, 90s. X root 3, and 2x. Cosine SOHCAHTOA is adjacent over hypotenuse. So I think it's going to be x over 2x, or if we simplify those, 1/2, right? Okay, so as we go through and do this, it becomes 2 divided by cosine of pi over 3, which is just 1/2, but don't forget the square. Well, working a little bit further, 1/2 times 1/2 is 1/4. And then it might help you to see this a little bit more by moving the 2 off to the side and putting 1 divided by 1/4, so that you can realize we're really just doing the reciprocal of 1/4, 4 over 1, which is 8. Yeah, definitely a bunch of little math bits in there. 3 problems to go, Team Fantastic. Let's get it. Show that all of the following statements are true given e to the x times sine of x is equal to f of x. Well, let's think about this function first. This function, I think, is continuous because e to the x is continuous, sine of x is continuous, and we know the multiplication of continuous functions is also continuous. That's good because it means instead of finding the limit, which can be a little bit abstract, it means we can just take 0 and plug it into our function, right? So let's try that one first. The limit as x approaches 0 of f of x is really just going to be found by replacing the x's with zeros. Any power to the, or any function to the 0th power is 1, and sine of 0 is 0. We get 0. That is true. We're going to write that out so we don't get that weird, like, is that true? Is that false? So yeah. So we're writing it out. True. Very exciting. Okay, and this was 1. let's go ahead and take a look at 2. I think in order to do 2, they wanted you to find the limit of the first derivative. So I think we'll probably have to find the first derivative first. Our first derivative, though, is a little complicated because it's e to the x times sine of x. So it looks like our product rule here. So let's do the derivative. Derivative of e to the x is itself. Keep sine of x the same. Plus in the product rule, keep e to the x the same, and do the derivative of sine, which is just plain old cosine, not negative cosine. The only time we get a negative is if you do the derivative of something that starts with c. Alright, well, then we wanted to find this limit here. We wanted to find the limit as x approaches 0 of f prime of x. Okay, well, if we do that, it really just means take the function up above and replace everything with 0. Not too terrible, is it? And we should be comfortable with the first part. We did that before. That was already 0, but we can write them out. We get 1 times 0 plus 1, and cosine of 0 is also 1. So I'm getting 0 plus 1, which is 1. I think our second one is also true. Okay, well, let's take a peek at the last one. The last one wants us to find the second derivative. Okay, here we go. Second derivative. Well, there are a couple different ways to do this. One way is that you can do the product rule here, and then a second product rule over here, so there'd be two different product rules. I'm going to try to avoid that, and I think by working with this up here, we might notice they each have e to the x in common. So I'm going to factor that out, and that's going to give me sine of x plus cosine of x. I think this might be a little less work. There are still two functions here. E to the x is multiplying times sine of x plus cosine of x, but I think our life is going to be a little easier. So let's take a peek. Derivative of the first function, product rule, is e to the x. We keep the second function the same, sine of x plus cosine of x. Okay, then we add because we're doing the product rule, and we do the derivative of the second function. Derivative of sine is cosine, and derivative of cosine is negative sine of x. Nothing terrible. When we want to go through and find the limit of this, because I think these are all still continuous, right? E, sine, and cosine are all still continuous functions. We can just evaluate them all at 0. So we get e to the 0th, and then sine of 0 minus cosine of 0. Probably should have skipped to the next step. Think I might run out of room. Oh well, something about 20/20 hindsight, but the odds of me re-recording this are extremely slim. We end up with 1 times, let's see, sine of 0 is 0 minus 1. That's going to be negative 1. Plus e to the 0 is 1. And then cosine of 0 is 1 minus 0. That's also 1. Okay? And then I'm looking at negative 1 plus 1. I think I made a mistake here somewhere, though. I don't remember so many negatives. Yeah, this should be a positive, shouldn't it? Yeah. I'm not sure where that negative came from. Sorry. 0 plus 1 is positive 1. There we go. And then we get 1 plus 1, which is 2, and this is also true. Okay, there we go. And it said, show that all of them are true. I think we did that through our amazing knowledge of calculus. 2 problems to go, superstars. Let's get to it. We are given that h of x is g of 2x divided by f of x, and we need to find h prime of 1. Whew. All right, then. Well, in order to find h prime of 1, I think we first need to find h prime of x. And this, to me, definitely looks like the quotient rule here, right? We have our top function and our bottom function. There is a pretty common mistake I see coming up in this quotient rule, so let's take a peek at it. H prime of x. Well, we do the derivative of the top function first, and realize the top function has two functions. It has an outer piece and an inner piece, and we need to watch that chain rule as we go through. So as we do the top function, g of 2x, we do g prime. That's the derivative of g, and we keep 2x the same, which means we need to multiply by the derivative of the inside to fulfill that chain rule. Then we multiply by the original other function, f of x. I think that's an f, right? Yep, f of x, perfect, we're winners. Minus in the quotient rule. Now keep the original first function the same, and multiply by the derivative of the second. Derivative of f is just f prime of x, nothing terrible there, divided by the denominator squared, f of x squared. Love that. Okay, well, I'm not going to clean this up because I don't want to, and it seems terrible. I'm not even sure if we can. Instead, we're going to skip right to what they're asking us to find, which is h prime of 1. Okay, well, I'm going to do a little simplification here. I'll move that 2 to the front. G prime of, well, 2 times 1 is just 2. And then we have f of 1, right, minus, and then g of 2x, well, 2 times 1 is 2, and f prime of 1, all divided by f of 1 squared. Okay, now how do we actually find all these values? Well, it did say use the graph, so we should probably use the graphs here. And we'll just go a bit at a time. I'm going to start with f of 1 and g of 2, just to make sure we're comfortable with those, and then I'll come back to these gaps. I'm going to leave those so I remember that I haven't done them yet. Divided by f of 1 squared. Okay, let's start with f of 1. F of 1 means go to the graph of f, go to an x value of 1, and find the corresponding y value. So I think this tells us that f of 1 is 4. Very nice. What about g of 2? Same idea, g of 2, go to the graph, go down. Looks like g of 2 is -1, right? Something like that. Cool, there's a minus in between them, not an extra space. And then we already found f of 1. We said f of 1 is 4. Cool. Takes care of our original functions. What about the primes? Well, g prime of 2, we're like, well, didn't we just find g of 2? Well, we found g of 2, but we didn't find g prime. We need to remember, what does a derivative measure about a graph? Well, the derivative measures the slope at that specific point. So if we wanted to measure g prime of 2, what it really means is, what is the slope of the graph right here? But luckily, this graph is a line. And one of the important concepts about a line is that it has the same slope anywhere. And you can see that in smaller and smaller pieces, right? If I start at this point up here and go here, this goes down 3 over 3. And of course, down 3 over 3 can reduce to, well, what does it reduce to? It reduces to down 1 over 1, right? It's -1 over 1. Or look, we could go even further. We could say, what if I started here and went to the next point? Well, this is down 1/2 over 1/2, and no matter how you do this, whatever point you start at, you'll go down and over the same amount. This all simplifies to -1, which tells you any point on this graph, no matter how close, will share the same slope of -1. We can apply the same thing to the graph of f. They want us to find f prime of 1. F prime of 1 means go here and take a look at the slope. Find the slope anywhere on this line. It looks like it is up 1 over 1. That is a slope of 1. Whew! Let's go ahead and finish this off. We have 2 times 4 times -1, that's -8. Minus, well, minus a negative makes it a +1. Divided by 16, I'm looking at -7 over 16. Remember that we try to gnaw on calculus. We approach it graphically. We just did that. Numerically, those are a lot of word problems we haven't seen too much of so forth. Algebraically from gnaw, we've done a lot of those algebraic, which is really a fancy way to say problems in equations. And then the last one is in a written manner, and I realized that I'd completely screwed that up. The written manner is, of course, word problems we haven't seen a lot of. The numerical one is what we're going to see to finish this off. Data presented numerically is almost always presented in a table like this, and there's actually whole classes on numerical methods or tabular data. So let's go ahead and finish off with a tabular data, a numerical problem. They are asking us to find k prime of 2, and rather show k prime of 2 equals 4/3. So let's start with our function. K of x, we know if we're going to find k prime of 2, we better find the derivative of k of x. But k of x has multiple pieces. It has an outer function, it has a next outermost function, and then it has an innermost function. And so I think we're going to be applying the chain rule probably 3 times here. K prime of x. Derivative of the outside function first, derivative of f, f prime. Easy. Keep the rest of it exactly the same. G of x squared. Sweet. We're not done yet though, because we just did the derivative of one part. Chain rule says next we do the derivative of the next outermost portion, which is g, so that becomes g prime. Keep the interior the same. Then we have to multiply by the derivative of what's still there, which is 2x. All right, not too terrible. Let's go ahead and find k prime of 2. So we'll use the space down here. K prime of 2 is going to be f prime of g of 2 squared, which I'm going to take some time and do, that's 4, times g prime of 2 squared, that's 4, times 2 times 2, that's again 4. All right. Well, what do we do from here? Oh, we yawn apparently, and then let's work all this out. I'm just going to do this inside piece first. I always like to start with the composed functions. You can do this in any order you want, but let's start with that g of 4. I think g of 4 is 1 over here, so that becomes a 1. And then I'm going to keep the rest of the problem the same. Again, I like to do kind of all this last part in one fell swoop. So let's go ahead and tackle all the rest. F prime of 1 is 2/3, okay. G prime of 4 is 1/2. Who picked this problem? What are these fractions? And then 4 is just 4. All right, well, can we clean any of these up? I think these 2's will cancel, and then we just multiply straight across and end up with 4/3. And that's what we were trying to show. So hopefully these problems were a little tricky for you, but at least understandable when I went through them. Because I've got to say, this is as hard as it gets. We don't get derivatives of functions like this that are any harder. In fact, these are probably harder than an average multiple choice question. The average multiple choice question may have you take an easier derivative, but these have all showed up. I've pulled these all from past exams or practice exams, so I do like to make sure I'm not sugarcoating anything for you. We want to practice at or even above the level of the test. If you can do that, you'll find the test very straightforward. So thank you again for all your hard work, and I'm excited to have you back for day 22 tomorrow.